Hello, welcome back. At this moment, we've finished all the analysis we need to know about a closed system. A closed system is the system where there's no mass transfer. Okay, so today we're going to move on to chapter 4, where we do analysis about control volume. By the way, what is a control volume? In the beginning of the class, we said we have two kinds of systems. One of them is called a closed system, where there's no mass transfer. And the second one is called a control volume, where there is mass transfer. Okay, so a typical control volume looks like this. You have a container. However, in this container, you have inlet and outlet. Therefore, you have mass going in or coming out. Based on the definition, if you have mass transfer going on for the system, which is within the dashed line, you call it control volume. We use CV short for control volume. Control volume. That's when you have mass transfer. The first thing we're going to discuss about a control volume is conservation of mass. Okay, conservation of mass. And then let's sketch a control volume first. A container with inlet and outlet. Draw the dashed line so people know everything inside is your system, and this system is a control volume. This is the inlet, and this is the outlet. Okay, so now we're going to talk about conservation of mass. How come we never talked about conservation of mass regarding a closed system? Because there's no need. If you have a closed system, there's no inlet, there's no outlet, the mass of your system will never change. It's very straightforward. However, when it comes to a control volume, the mass of your control volume may change. So for example, if you have Mi mass at inlet, you have this much mass Mi going into your system at inlet. At the same time, you also have this much of mass Me coming out of the system at the outlet. What's going to happen to the mass of your control volume, MCV? So Mi goes into your system. However, Me leaves your system, so we use minus sign. And what's going to happen to the rest? So for example, if Mi is equal to 10 kilogram, and then Me is equal to 8 kilogram. So 10 kilogram goes into your system, and then 8 kilogram comes out of the system. Where does the 2 kilogram go? The 2 kilogram will stay inside and be added to the mass of your control volume. So 2 kilogram is the change of the mass of the control volume. We can use another analogy. Mi is the money you deposit, and Me is the money you withdraw. So for example, if you would deposit $100 and then you withdraw $80, where does the $20 go? $20 is the change of your bank account balance. So this is the equation. This is called conservation of mass equation. But this is not usually the format we use because the fluid is always flowing. So we do not usually use M, we use something different. What is it? We're going to divide every term by time. So this equation becomes Mi over time minus Me over time, and right hand side becomes delta MCV over time. Okay, and then M over T has a name. M over T, we call it M dot. So M dot I minus M dot E. And right hand side becomes dMCV, derivative MCV over dt, derivative time. You can change delta to t when the step length is very small after you take calculus class. Okay, and then the syntax with a dot on top of it is always the same in this class. Remember, for heat transfer rate, we use Q dot, which is Q over time. For power, which is work over time, we use W dot. So if you ever see a dot on top of a letter, that means divided by time. Okay, so this is the conservation of mass equation if you have a control volume. Okay, so now let's talk about it more. First of all, m dot has a name. M dot is called mass flow rate. Mass flow rate. And what should be the SI unit for m dot? Because m dot is equal to m over time, the SI unit for m is kilogram. Divided by time, the SI unit for time is second. So kilogram per second is the SI unit for mass flow rate m dot. It means how much mass is transferred per unit time, which is per second. Okay, and then how do we calculate mass flow rate? We can derive an equation for mass flow rate. We start from the definition. M dot is defined as mass over time. And then how do we calculate mass? We use density and times volume over time. Density multiplied by volume, that is mass. So let's make a note. The V here is volume. Okay, and now let's continue. Keep rho and keep T. How do we calculate volume? How do we calculate the volume of the mass that goes into the system? So for example, you have this much mass at inlet going inside. How do we calculate the volume? How do we calculate the volume? And this goes back to geometry. How do we calculate the volume is area, this is area, multiplied by the length. Area multiplied by the length gives you volume. Area is the cross-sectional area of the inlet. Okay, so let's continue. We can rewrite volume into cross-sectional area of the inlet or outlet multiplied by the length. Okay, so now let's continue. Rho A over T. Let's keep rho A and T. Now let's calculate length. How do you calculate the length that the fluid has traveled by? How do you calculate, in other words, distance? Distance is equal to velocity multiplied by time. And here, V means velocity. It's not volume anymore. So now what do you notice? We can actually cancel time. So the only thing that is left is rho VA. Okay, so finally, our equation for mass flow rate m dot is rho VA. Okay, where rho is density, density of the fluid. The unit is kilogram per cubic meter. And V here is velocity, velocity of the fluid. The unit is meter per second. And A is the cross-sectional area of either the inlet or outlet. If you are calculating the mass flow rate at the inlet, you use A at the inlet. If you're calculating the mass flow rate at the outlet, you use the A at the outlet. Okay, so that is mass flow rate. And in addition, we introduce something very similar. We introduce a new Q. It is volume flow rate. It can be a little confusing here because usually we use Q for heat transfer, but in the textbook, We also use Q for volume flow rate, so you need to read the context in order to understand what Q stands for. Okay, what is the definition of volume flow rate? It's pretty straightforward. Volume flow rate is equal to mass flow rate divided by density. And we know mass flow rate is equal to rho VA, so we plug in rho VA divided by rho, so what is left is V times A. Volume flow rate Q can be calculated by VA. V is velocity, A is cross-sectional area. The unit for Q is cubic meter per second. Okay, and keep that in mind. There's only conservation of mass. There's no such thing as conservation of volume. Okay,